So, what are the techniques which we can be used for evaluating the behavior of the PCM material? So, techniques for evaluating the behavior of PCM material. So, we can use two techniques here. So, first one is differential scanning calorimetry. So, we can call it DSC, and other is gravitometric method. So by DSC we can raise the temperature and we can detect the phase transformation, and we can measure enthalpy change provided by the transition. So by DSC we raise the temperature and detect phase transformation and we can measure the enthalpy change provided by the transition. So if we perform DSC over several cycles, then we get the thermal stability. So if we perform DSC over several cycles, we can get thermal stability. Now another possibility is to measure the thermal stability by gravitometric, by this method basically. So we can perform several tests and see if expansion or contraction of your material remains stable. So basically we measure expansion or contraction of a material remain stable. And if at the end our material has same characteristics at the beginning, so at the end material should have same characteristics which was at beginning. So we can have some problems related to the system. So let me draw one diagram here. Let me draw two diagrams, not one diagram. Okay, so this is the melting peak graph, melting peak, and this is solidification peak. On x-axis we should have temperature in degrees Celsius. Here we should have temperature in degrees Celsius. and on a y-axis we should have heat flow in joule per gram, heat flow joule per gram. Now this graph should look something like this. For first cycle, suppose we have 4 cycles. One we have something like this. For cycle 9 we should have something like this. For cycle 12 we should have something like this. For cycle 12 we should have something like this. For cycle 100 we should have something like this. For cycle 104 we should have something like this. For cycle 200 we should have something like this. Okay, enough. So if you look at the melting peak, so basically if you're looking at this graph, melting peak, so only one melting peak is stable. So this material can be considered quite good for melting. Now if we look at the solidification curve, let me draw solidification curve first. So for different cycles in similar fashion. So for first cycle, suppose I have like this again. Okay, for cycle 2 I have something like this. Okay, for cycle 3 something like this. Okay, so here we are having coarsening of fine particles. And here we have having reduction of coarse particles. So if we look at the solidification curves, we notice something strange. So typically when we have DSC, we have temperature, enthalpy of melting. Now if we reverse the temperature, we have solidification. So we can have change in degree of undercooling. So solidification of tin inside aluminum is related to different crystallographic orientations. So if liquid tin interacts with aluminum having specific orientation, it will solidify in different ways. And it is also related to the dimension of silicon particles. So we have a composite signal which spreads over wider temperature range. So we have composite signals which spreads over wider temperature range. So is it good or is it bad? So if you have shorter temperature window when it's melting and larger temperature window when solidifying, so it is not strictly good nor strictly bad. It is bad if process once we solidify, temperature range in which solidification is so large that we are not able to have complete solidification of our system before the cycle starts. And it can be good if we don't need to have sudden release in it, and we just want to absorb excess heat and then release it slowly, so to control it little bit better of temperature range. So we should know the temperature range which we want to work in. So let me close this last lecture of this thing. Thank you.